Welcome, everyone, to the final session of this all-new, all-virtual CPPCon 2020. I hope you've enjoyed the program as much as I have, and we're now in our final set of talks. So here's what to expect. Most of it's happening right here in this all-of room, or equivalently, if you're in the overflow room, you'll see the same thing. For the next hour or so, I'll be giving this talk, and then right here, stay right here for John Kalb, who'll come in and he'll give us the conference wrap up, including some interesting tidbits about next year and things you may not have known, what you can do with this conference still, what to expect. And then we're going to come back and use the rest of this half hour here for Q&A for my talk. So this talk will have Q&A, and it'll be all in this room. So stick around, and after John, we're going to go up to the hour to do Q&A. After that, you can either hang out here and listen to the final set from the Jim Basnight Band, the CPPCon House Band. Thanks again to them for playing for us this week from the Seattle area. Or you can go to a Zoom meeting if you're interested in planning or maybe interested in wanting to contribute to CPPCon or just see the ideas that are going around or give feedback. You can find the Zoom meeting on Sched that will be happening at 1500 Denver time. So that's what's going to happen. For the next hour, let's talk about actually measuring stuff, because every single one of us knows C++ is too complex. That's a given, but that's qualitative. It's not quantitative. And yes, we can all give examples and experiences, but that's also not quantitative. I can't count those directly. Wouldn't it be nice if we could count it and also see how much is accidental, that is non-essential complexity? So let's define some terms and give some motivation. Complexity matters because as long as any system is more complex than we need it to be, we are paying taxes using it. And it may not seem like a huge tax on one day or on 1 week, but as we keep paying it, it's going to keep on costing us as we read and write code, as we deal with bug reports and outages and even vulnerabilities and exploits, as we wait for our tools, as we have to teach people. So we can benefit from reducing complexity in these and other ways. So for the first part of this talk, I'd like to give a shout out to Barbara McClintock. She is a famous scientist and Nobel laureate who was famous for actually looking to see what happens in DNA and showed DNA transposition and how that worked by empirically measuring. So let's do what Dr. McClintock did and empirically catalog, classify, and count C++'s complexity. Well, how are we going to do that? First, let's remember what Fred Brooks distinguished as essential versus accidental complexity. Essential complexity is inherent in the problem domain. So if you build a systems programming language, say, that values efficiency and it wants to give modern abstractions like the kind we're used to, any language, regardless of the syntax or the details, is going to have to expose something like compile time polymorphism, something like virtual function dispatch. So there are certain essential things, or encapsulated types. And the details can vary from one to the other, but there's going to be some essential kind of abstraction in solving a given problem, that no matter what the detailed solution is, you're going to find it. Where we all trip up, and every language does this, is the accidental complexity. It's where this particular solution, boy, it sure has more knobs, or it falls over, or the knobs come off in our hands sometimes, and we have to jam it back in more than we would like it to, and more than it needs to. And we'll call that, Fred calls that, accidental complexity, and it's an artifact of this specific solution. And I'm giving you the picture of a push sign. When you see a push sign on a door, when you see a sign on almost anything that tells you how to use it, almost certainly there is accidental complexity, and there's a UX problem as well. But there's something that doesn't work like is easy to learn, like you would expect it to, and often is more complex, and then accidental complexity enters the picture. Now, the reason I mention signs is because signs often tell us where the accidental complexity is. So if we could count the signs for C++, maybe we could count the accidental complexity in an empirical, measurable way. So I have bad news and really good news, and they're the same thing. C++ has probably the largest, the richest body of coding standards and guidance on how to use of any programming language. I haven't actually counted compared to other programming languages, but it's popular and it's complicated, and it shows in all the stuff that we've written down to teach and learn. So I've actually gone through and counted so far in what's on the left-hand side, and I'll continue on the right-hand side, to actually, in each book, and this has taken months and months of work spread over years, to catalog what is each piece of advice. So in Scott Meyer's items, it's not just per item. Each item may have several guidelines of do this, don't do that, or do this a certain way. And now, by getting a list of rules, we can now make a spreadsheet, which I did, thank you, Excel, and start to quantify it and to classify it. So the first thing I did was to classify these cataloged rules. The first granular level of classification was, are they language or library rules? And most of them were about the language, but there were some about the standard library. We'll focus on the language rules here. I also found a few that I'm going to discard because they're general rules, like, for instance, use a version control system. Okay, that's good advice, but it's not specific to C++ or programming languages in any way, not even programming. You want to do that for Word documents. So I'm omitting those. And 10 were even, in my opinion, you may differ, just wrong rules. But even them I found informative because often they arose because the language created a pitfall or a confusion or an ambiguity that somebody resolved in a way that I happen to disagree with. But it wasn't only their fault. It was because there was a complexity. So let's look at the language rules. Of the 533 individual language rules I classified, I then went to see which ones are accidental versus essential, and also which ones can we improve on, because even essential ones we can improve on. I found that over 360 were accidental complexity, that another language like C++ that solves the same feature could do in a simpler way, that didn't have this problem that C++ has that we have to teach. And that were improvable because, look, here's how it could be done in an existing or hypothetical other language. There was a way to do better. I found that almost 150 were essential. That is, you're going to have something like this in any language that solves this kind of problem, but we can still do better. It was needlessly complex. The knobs were too ornate, or there were too many of them. And finally, I found 25 that were, yes, you would pretty much have to take this guideline out of this C++ book, change C++ to C# or something like that, and you'd teach it almost verbatim with just minor changes like that. And C++ does, in fact, have such beautifully designed features. At least those 25 rules fall in that category. Now, the first thing I want to point out, just from the shape of that pie chart and its proportions, Fred Brooks also famously concluded there was no silver bullet. There was no single thing we could do in technology, or he also included management techniques, that by itself could give you an order of magnitude, a 10x improvement. So we often quote that, but it's worth looking at why he said that. That's the conclusion, but he also states, like a good scientist, his premise. And his premise right before that was, how much of what software engineers do now is still devoted to the accidental as opposed to the essential? Unless that's 90%, you can drive it to zero and you won't get a 10x improvement. But if you remember the slide we just saw, if you do have 90% improvable accidental or improvable complexity, then you have a big problem, but you also have a big opportunity. And that is where we are. We have such an opportunity where by evolving the language, we could, in principle, address this much just because by cataloging, we've measured this much is accidental or improvable essential. Bjarne Stroustrup has famously said for some at least 16 years now, since Design and Evolution of C++, that in fact this could be possible. An equivalently powerful language that is good at all the things C++ is good at, but is simpler, could be done about 10x smaller. And notice what he says, it would be through generalization, which is absolutely true. And I would expand on that a little bit by making general orthogonal features that compose well, so you get maybe fewer, simpler features, but a combinatorial explosion of things you can express, and that's where your expressive power is retained. And it's also by making those orthogonal things directly express what you're trying to do, usually instead of how to do it, which is usually a messier recipe. So let's pursue that thought. And when I went through and I took a first cut classification into major categories of these different sources of complexity that we could improve, by far the biggest one, the category, was multiple ways to say the same thing. So C++ is famous for this kind of thing. But then as we go through, there are a few other large buckets that we can address. The one at the bottom right, kind of class authoring conventions. So that's a subject of a different talk I've already given at CPPCon, and the metaclasses paper directly expressing the intent for how we write a class. But we're going to focus on different ones today. So with that breakdown, we commonly hear C++ is too complex. And what I've tried to do is to empirically catalog, classify, and count. So it's no longer anecdata or just anecdotes, but that we can actually say, okay, C++ is this much more complex. And I think that we can empirically make the case that Bjarne was correct and is correct when he says that C++ is about 10 times as complex as it needs to be. For various reasons, backward C compatibility and other things. But that's a statement that Bjarne has made qualitatively based on his deep experience, and that I think is directly supported in the empirical cataloging that I've been doing. So now we're going to switch to a different kind of scientist. And the nice thing about mad scientists is they have crazy ideas. And every so often, at least in the movies, they can build a flying time machine that looks like a DeLorean. So we are in this mode where, as C++ developers, so often we say, well, yes, but we can't really do anything about it. We can only make incremental improvements. So let me, in the rest of this talk, try to demonstrate a 23%, and then when you add it to metaclasses, a 30% reduction, which actually gets us 1/3 of the way, roughly, to a 10x improvement. And what I'm about to show is experimental, but we're also going to see prototypes in Godbold. So when we look at this picture that we just discussed, and we focus on these two wedges of the pie, about 23% of all the guidance that I've cataloged so far have been about how to pass parameters, 16%, and how to initialize variables, 7%. Now, some of it's repetitive because it turns out that multiple books talk about how to pass parameters, but that in itself is an indicator because we don't have to dedupe these rules. The mere fact that other books continue to give the advice, even though it's already in print, and they often don't give the same advice, but they give divergent or incompatible advice, then we have a measure that this is something that the community has voted with its feet to say, here is what is important to teach about C++. So let's talk about first how to pass parameters. Here's what we teach today. It's too much to go into it. I'm not going to spend a lot of time on it. We'll see it sort of as we go with the today examples, but I'm going to focus on the simpler thing that we can do in the future. But this is roughly what we teach today, and it is not complete. If you want examples of where it's not complete, I have a link to a GitHub repo that I've just published that contains a draft paper about this material and compilable links to examples you can try on the working implementation. But the paper explains more about why even this is not complete. That's because we are saying how to pass parameters. Oh, pass this one by value, pass this one by reference. Oh, what kind of reference should we use? We're specifying the recipe, not the intent. If we could enable expressing the intent, what do I want to use this parameter for? Then I could teach, I believe, just this. And if this were added to C++, then I believe that this is fully expressive and fully subsumes what we do today in the use cases I've seen so far. And I would never have to teach anything more than this. Now, there will be more code than this in the rest of the talk. But most of what comes up in these next slides is about explaining the complicated thing we have today, because that's what we all know and are used to. And to help see how does that relate to this proposal. This proposal parts, the code will always be simple. What we do today that's equivalent is more complex. But I think I can teach parameter passing in this slide by what's shown here and get rid of roughly 23% of today's literature if only we could do that. But let's dig in and see, well, yeah, this is too simple. And in just says, give me an X I can read from. In out, an X I can read and write. Out is an object I will write to. Specifically, I'll assign that's how we say assignment is to set all the salient values of, or one I'll move from, or one that I'll forward to other code. And that's it. And one question I've received is this exposing implementation detail? No, except what's necessary for the contract with the caller, because this is information both the caller and the callee need to know, for instance, at the call site, will there be a side effect on my argument? Oh, I'm passing it to an in parameter. It's going to only read. There will be no side effect through that use of my argument. I'm going to use some terms, definite first use and definite last use, through the rest of this talk. Here is explaining them in one slide. Let's say I have a local variable parameter, includes a parameter, and I want to say, what's the first use of X? So on any execution path through this function, what is definitely going to always be the first use of X? And that's easy. It's in the very first line. You can't execute non-exceptionally through this function without your path going through that line of code first and seeing that as its first use of X. So that's a definite first use of X. Where's the definite last use of X? Well, there are two. And that's okay, because any execution of this function will take one branch or the other. And if it takes the first one, then x.hold is the last use of X that it will encounter in this function. And if it takes the else, then the cout X is the last use in that function, definitely. If you get to that line, it's the last use of X. There are no more. What about Y? Y doesn't have a definite first use, because if you process Y, well, you might do that on some paths, and then it is a first use on that path, but it's not definitely always going to be a first use. It does have a definite last use, and that is transfer Y. With that in hand, let's start defining in, out, move, and forward. The 5 things I think you need to know to do all parameter passing in C++. The most complicated, as it turns out, and we'll demo at the end, is in. So what we teach today, and what is automated here in this abstraction in the language, is if the type is cheap to copy, like an int, then pass by copy. That's what we already teach people today. We just say in, do that all the time. Otherwise, pass it through an indirection, as if by pointer or reference. So that's the calling convention. If you cracked open the assembly, you would see a value or essentially a pointer, an address on the stack. What can I pass to the in parameter? Any initialized object. It can be an L value or an R value. Inside the callee, I can treat it as a const L value because it could be const or non-const, the argument, but in says I'm only going to read from it, so I treat it as a const L value, as const for my purposes. That's implicit. Except that if you passed me an R value, then any definite last use that tries to copy from it will treat it as an R value. In other words, can move from it. Let's see how that works. So today, we would pass an int by value. This is what we teach people today. F1 takes an int, an in int, pass it by value. Oh, it takes an in string or something else that's more complex. Oh, well, then take it by const reference. And if you're going to take a copy and move is cheaper for that type, you want to optimize for R values, then also overload for R value reference. And by the way, remember to write std move on that, and remember to write std move only once on the definite last use of the parameter. So that's what we teach people to write ad hoc today. If you write a template, it's harder. I'll show you what you could do and what, say, a very small number of people like standard library implementers do to follow the advice, oh, if T is small, pass it by value, etc. Mostly we just say, hey, template, yeah, const ref, sure, let's do that. There are a few who say by value, and that's a discussion you'll see me address in my very first CPPCon keynote 2014, so you can find that on YouTube. But mostly they just say, const ref, because it's hard to overload to pass by value. You have to enable if or requires to do that, and it's even harder to overload for R values, but I'll show you how you can pretty much do it. All of these equivalently, in this proposal, you would just write in int is all you write, and it automatically passes by value. In X, if X is not cheap to copy, automatically passes by, as if by const ref. And if you give it an R value argument at a given call site, will move when it calls G. And the same thing is true of a template. I don't have to worry about if it's a template. I don't have to specialize. I don't have to enable if it requires anything. Whatever the type is, this is what in will do. So it's efficient. We're always going to copy values when that's cheap, and we're going to move from R values, and it's easy to write and get that effect. So that was in. Now let's talk about in out. This one's actually pretty simple. For in out, we just pass basically the address of the object so that we can read from it and write to the original object in C2. We could actually, and we're contemplating, pass in and out by value as well for this as an optimization. You'll see that mentioned in the paper. That's a possible extension, but right now the paper says that we pass by pointer. You have to pass an initialized non-const object so that we can write to it, and then we actually will treat it as that non-const object. You just use it as you would normally, but we can also give you a rule because you said I want an in-out parameter. We can now tell you if there's no path on the function that ever writes to it, that's not what you said you wanted, and we can give a diagnostic so that because you've expressed your intent, we can give you a higher quality of code where if it compiles, it does what you said, which is the holy grail of programming languages. If it compiles, it meets my expectations. So today we write in out as basically xref, sometimes x star. And in F1, we're fine. We read the value, that's fine. We write the value, that's fine. But in F2, we forgot to write to x, and today we don't get an error. Maybe your static analysis tool will give that. And it turns out, you'll see on the next slide, you spell it the out parameter exactly the same way. So we can't distinguish between in out and out unless you're using static analysis extensions that put annotations like in out, and these exist and are used to disambiguate this that the language does not. But in out, this is what you would write. And this is the simple case where the proposed equivalent is just to, instead of that ampersand, just write in out. But it gives you more than just nicer syntax if you don't like ampersands, it also makes sure that you do assign to the value. And it's simple and clear because now I can distinguish this from out. So that's really all to say about in out, is I can read and write from X. But what if it's only out? Pretty much the same, except that I require that every path must have a definite first use that assigns a value to X. And remember, assignment in C++ is our typical way of saying write to all the salient parts of, or passes it to another out param, because this will compose and that will do the same thing. So today, we can't say out except as a comment. If we, in the first line, g of x, happen to read from the input value, that kind of works. Even if the input value is garbage or sensitive data, somebody's password, we can do that, even because we can't say out only directly. And we can't flag that we've failed to actually do the out part either, to write to something, unless we have a tool that gives a warning, and that's non-portable, because we have to have a non-standard out annotation and a tool that knows what we mean, because in the language we can't express this. The proposed equivalent is just to say out. It would be a compile time error, therefore green. Green is for errors when the errors are good and desired. You would get an error if you tried to read from X before writing to it. You are required to write to it, and then it's okay to read from it because you're reading a value you set. You're not using the in value, which you said you weren't going to use. Simple and safe and clear. Move also passes by indirection. Actually, in the implementation, this one has already been optimized to also pass int say by value. So if you say move int, it will actually do an int by value under the covers, which is an optimization over what we do in C++ today for move templates. And what we're going to do is require that this R value, we accept only R values, and that we pass them to another move or R value use. So today, the way we write this in a non-template is to say, oh, we use a R value reference, which is spelled double ampersand when the type is not a template parameter type, it's a concrete type, then it's an R value reference. And then we remember to write std move. If you want to move a template parameter type, well, you can't just write trefref, because that actually means something different in C++. Sorry. So what you do, I won't go into the details of why, but thank you, Nico Yosudis, for teaching me this incantation. It turns out that the incantation std is reference v happens to be the right thing for you here to say accept only R values. Just trust it. And then instead of std move, yeah, you really should be saying std forward, and then you have to explain why you wrote that instead of std move, because you're really doing std move. But this is pretty close. It's not an exact way to write a move templated parameter in C++, because you didn't actually write move, but it's very close. And I believe this is correct today, but I don't want to teach that. I just want to teach template, non-template, don't care. Big type, small type, int, don't care. Just write move. And they all work the same. Finally, forward. Again, this one takes any object, just like a perfect forwarder today, but is much easier to use than a perfect forwarder. We're allowed to look at the value if we want to read from it, say, because maybe the forwarding function, we're writing code that's in the middle between a caller and callee and just passes things along, but it may want to look at it, say, to log the value. That's what we commonly do in forwarding situations. So we can read from it, const uses, but every definite last use is going to, like today's perfect forwarding pattern, preserve the constness and whether it's an L or R value, whether it's a temporary or not, basically. So today, the way we write that is the forwarding pattern, which looks like this. For a templated type, that's fine. Now, if you want to do this for a non-templated type, you still have to write a template, because that's the way you write a forwarder in C++. And then you say, through requires or enable if, you say, well, it's got to be an X. And there are different trade-offs to say whether you say is convertible or is same. And if you say is same, you have to say remove cbref, because you just do. But this is how you would write it for a concrete type, which, as far as I can tell, nobody does. Nobody uses this to forward concrete types. It's difficult, but it's just possible. Here in this proposal, it's easy. I just say forward the type. It doesn't matter whether it's a template parameter type, a concrete name type, and I don't have to make it a template just to forward something if I'm forwarding a concrete type. This is, by the way, really important because you'll have noticed that several times now with move, especially, and with forward, but also with in when we overload it with move, I've said, today we have to write a template sometimes or get out of a template sometimes instead of writing the code normally. And Bjarne Strustrup has long made the important stake in the ground that he would like to see less divergence and a convergence in regular code and templated code, and to remove the differences. This helps directly to remove the differences between writing a template and writing a non-template code and makes them the same. So I do agree with that that's important. So now, having looked at those, let's look at some examples. And you can find these at cppx.godbolt.org, which is graciously made available by Matt Godbolt. Thank you very much, Matt. And the person who's done the hard work of implementing this, as well as several other of the proposals I've spoken about here at CPPCon, you can find thanks to Andrew Sutton, who has done the implementation of these parameters in particular. So let's now switch to these examples. And as we do that, I wanted to show you a couple of helpers first. So the first helper that you're going to see me use, sometimes in the body I'll want to say, and let's say we copy from this parameter. So I'll just call copy from. Here's a really simple way to write in C++20, write a function that just takes any number of parameters and just attempts to copy construct each one. And of course, if it gets an R value, it will move instead. Just take a variadic, generic set of variables by value. That's all that does. Auto ... Each variable, each parameter can be a different type. It's auto and it's passed by value. Kind of nice. I want to see what's going on. I want to see where the copy constructors and the move assignments are in particular. So what I've just put together as just enough to get the testing done is I've got this global history string, just for the purposes of the sandbox testing. And I've got a function which will, again, it's using C++20 code. It will take any functor, any invocable thing by value, and it will run it. But first it will clear the history, and then this thing will, as a side effect, write things into the history, and then it will return for convenience the history that was generated from running that F. If you haven't seen this syntax before, history equals brace brace, that's a modern way to say default initialization because, well, that's how it works. So I find that very useful. So that just clears out the string, runs it, and returns the history that was generated by that execution. And now, in order to see the copying and so forth, I've got this noisy helper, which just basically writes out to the history string when you call the default constructor destructor, copy, move, and otherwise just delegates to the thing you wrap. So that way I've instrumented the special member functions so I can see what they're doing. And I can then write test cases, which you can find in the GitHub repo. You'll see the link out at the end. So here's the first demo. This is the really simple one. We hope that there is nothing magical to see here. All it's saying is today, old, we say pass an individual int. Oh, you pass that by value. And then in this new proposed way, you would say in int I, we would hope the code gen is the same. So let's take a look. And here, if we look in Godbolt, there's our copy from helper. Here is old in, it takes an int by value, just the way we teach people to write it today. And you'll see here is the code gen push call pop. New in, which differs because it's using this new in implementation. Now it's an int, so it ought to pass it by value. The code gen in this case is the same, push call pop. So that's a good thing. That's the first demo. So you've written in, but now you might be saying, oh, look, that's more verbose. I had to write 2 more characters and a space. True. All the other examples will be increasingly in the other direction. Let's now, instead of an int, pass a string. And in this case, capital S string is just a noisy of stood string. That's all it is. So the current way I would write this is I would overload on constref and R value reference. And in the first case, I would copy from S, and in the second one, I would copy from std move of S. That's what we teach people. And now we'll compare that to the new way of saying just in string S. So let's take a look at that example. So here we have old in, which is the overload set. I've got new in, and the way I've been testing these is to say, okay, here's where I call my run history function, where I'm just going to run the history of two things, the old thing and the new thing, and then print their histories and compare them side by side. And so what I'm going to do is for 3 different cases, starting with a non-trivial L value. So look, there it is. There's an L value, X. It's a named variable. That's an L value. I'm going to do the same call, old in expressed the current way, and new in the new way with the same argument, X, and see what they do. Then I'm going to do it with a std move of X, and then finally with a fully pure R value, a real temporary string. On the right-hand side, you'll see that for a non-trivial L value, we in fact are doing what we expect. We're writing the copy constructor, doing the copy in both cases, because we passed a string by value. It's a named string, so we're going to copy it into the copy from function. But for the other two, you'll notice that we correctly do a move in both cases. So what this means is that in both cases, including in the in string case, we see, oh, this is an R value argument. Both of these are R values. That means at this definite last use, we're going to move rather instead of copy. But I didn't have to write an overload to say that. I didn't have to write std move anywhere. I just wrote a function, which now I can take the address of because it's on an overload set. I just wrote a function that says, oh, I want an in string, where if I copy it and you pass me an R value, I'll just naturally move from it. Because that's what we've already learned is the right thing to do. It's what we teach people to do. And so on the right, you can see that that's in fact what this implementation does. So that's demo number 2. And you'll notice that I'm putting Godbolt links on each of these so you can see and try each of these yourself and try variations. But now let's do something a little harder. 2 in parameters. Well, 2 parameters, that doesn't seem very hard, but if we follow the advice in this case, we take 2 in strings and we do what we tell people to do today. If you copy from it, you consider overloading for R values. Well, then what's going to end up happening is that you write this combinatorial, in this case 4 set of overloads, one for string constref, once for R value constref, once for constref R value, and once for R value R value. Instead, I would like to be able to just write, I want 2 in strings, please. Please do the right thing, sir. So this example looks like this. And again, the Godbolt link is there. So here's the overload set we write today. Here's what I would like to write instead. And here's what Andrew Sutton's prototype compiler does. Again, I'm doing the same compare function just to get the histories of 2 calls. And I'm going to do 2 L values, L value and R value and L value, and R value and R value, all the combinations. And old in does exactly what we think. It does copy, 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 move, move, copy, move, move. The nice thing is, when you look at these, let me try to use a different, there we go. When you look at these, so does new in. But all I had to do was write in string, and when I copy from them in the body, it automatically does the copy, copy for 2 L values, copy, move for L value, R value, move, move for 2 R values at these definite last uses of S1 and S2. Now, it's more than just that it's simpler to write this code. The fact that I'm writing all these overloads actually generates bigger binaries, bigger object code. And you can look at yourself on Godbolt, and I was going to scroll through and show it to you. You can do that yourself. Instead, I took a screenshot. And here is the actual assembly generated on Godbolt for this example. The larger piece of code here. If you zoom in, you might be able to see it, or it might be pixelated in the slides, but you can see it yourself online, is for these 4 overloads. It's about 250 lines. And for this function, which does the same thing, it's 120. So this is kind of nice because you remember that we already said we get the same optimization, move from R values in any combination. So they're equal on performance at runtime. They're new in wins on being easier to write for programmers, so on simplicity, and it wins on executable size, on the object file size. Try more examples yourself and see for yourself how the object code varies. But to me, this is a win-win-win because it's just as fast, way simpler to write, and gives me smaller object files, which usually we like. Now, you might say, how often do people do this? In fact, I wondered, how often do people really, for 2 in parameters, do this const ref ref ref, ref ref const ref, ref 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 ref, const ref overloading? So I asked Twitter a few days ago, I asked, have you ever, and so this is going to overcount, because it's going to count anybody who's ever done it once in their careers. But I was curious because I was thinking the answer might be like 1 out of 10 have ever written overloads like this to optimize for R value arguments. I mean, I know standard library implementers do this, but for my Twitter followers and the people they forwarded to, have you ever done this? Asking for a friend and for this talk. I was kind of surprised that 25%, that to me, that was high of people who've done that. But in the comments that followed, I found some interesting information as well. So just a few highlights. One of them was, don't remind me, I've done it with 4 arguments. And we know what 2 to the 4th looks like. And someone else said, assuming X isn't templated, that's right, because you can't actually do it this simply if X isn't a template. It's harder, as we already saw. This is the easy version today. Assuming X isn't templated, yeah, I've had to do that. I used a macro. So this is an example of what complexity forces people to do instead. Another example of what people do instead is they say, I'm not going to do that at all. I'm just going to bail and use perfect forwarding, which means writing a template. It's less clear because perfect forwarding is an expert level feature. And it's changing the problem because perfect forwarding doesn't express in. This isn't actually saying the same thing anymore, but macros and perfect forwarding is what this drives people toward, even for when it's just 2 parameters, or it drives people to quit C++. Maybe not this specific thing, but this being the last straw on the camel's back before they just break away from C++. However, I have to say, my very favorite answer, which really surprised me, was this one. Thank you, Marcelo. I'm not even going to try to show you what this looks like with 3 in parameters of concrete types. Just press Control-C, Control-V a few times. Make sure you write stood move in all the right places. I had to, even for the 2 parameters, I had to triple check my code to make sure I was writing it correctly. Instead, I would just like to tack on a 3rd in string parameter. Thank you very much, and not have to overload. But now let's look at templates. Let's go back to a simpler version of the example with just 1 in parameter, but of a templated type. Turns out you have to write this nest of things. Basically, you're saying, if I should pass by value, so I should pass by value if it's trivially copyable and the size is less than something. Let's just say, you can make your own predicate here. If I should pass by value, so I'm going to use C++20 requires, or if you don't have that, use enable if, to use this overloaded template, which passes by value. Great. Otherwise, if I shouldn't pass by value, I'll pass by const ref. Great. And here's the fun one. Remember overloading for R values, and especially in templates, you may want to do that because I'm going to copy. And T could very easily be cheaper to move than to copy. So I really am incentivized to always write this one for templates that copy an in parameter. I then additionally write this incantation that Nico Yosudis taught me. And it happens to be the right thing here to turn this into a move. And I still write forward instead of move, but we'll call this close enough. Instead, I would like to just write in auto T. Now, let me for a moment defend this, because one of the first things you're going to say is, hey, shouldn't this have at least one extra line, template type name T in TT? Yeah, that works too. It's still way better. But I can actually use auto here where I can't in today's guidance. So today, this auto, this with just C++20 for an implicit template parameter, I could write this here. It turns out that, in fact, I didn't know exactly how to write it, so I asked the world's experts. So thank you again to Ville Voutilainen and to Andrew Sutton for, over the course of several emails, teaching me and learning how to write this using auto instead of template type name T. You do not just change angle T to angle decal type of little t. That is not correct. And it's still more verbose. So I think it's a fair comparison to say, no, I'm going to show this today's guidance with template type name T, and I'm going to show this one with the natural way you can write it in C++20, because now it is natural to write, and it is feasible to write with this new proposed in qualifier. But if you still aren't convinced, fine, I'll take the comparison with this any day of the week, and it still wins hands down. We're going to again compare current with proposed. We're going to do a trivial L value, a non-trivial L value, non-trivial R values of two flavors to make sure we move from them. And again, we see no history instrumentation for the int because I can't instrument an int and keep it trivial. But if you look at the cogen, as we saw already, it's the same, passing int by value. Otherwise, I copy from the L value and I move from the two flavors of R value cases. But all I had to write was this, not this. I'm not going to demo how to do a templated version with, say, 3 parameters. You can go ahead and try it. We know how to do it, but cut and paste is your friend, and make sure that you tweak everything correctly. And I don't think anybody will complain it's maintainable. But if I wanted to do that for this new style, I would just say in auto, in auto, in auto, and it would work. In fact, let's do not 3 parameters, but 6, just because. This will be our last demo. And I'm not going to show today's way of doing it. I'm just going to show here is a template with 6 generic parameters, and I want to pass trivial ones by value, the cheap to copy ones by value, otherwise by effectively const reference, and also effectively overload for, but it's not really an overload here, to move from R values. And I'm going to put a few line breaks in the history just to make it easier to read, and I'm going to copy from each of these variables. I'm just going to group them just for yucks. And now I've got an int, a string, and various strings, and now we're going to have this call site, new in, we're going to pass an int, a string, move S2, S3, 42, and then a string temporary. So the first thing we're going to do is, as we pass these all by in, is we're going to copy from A and B. So first we see the default constructor outside the call, that's creating this string temporary at the call site. Then we get inside the function, and first thing we do is we execute copy from A comma B. A and B in this case are I and S and int, so we should see nothing in the history for that because we pass that by value and it's not instrumented. And we should see S is an L value, so we should copy from that. So we should see a copy, and sure enough we do. We see in the copy from call, we see the copy constructor and then the destructor of that object. And that's as we copy from B. All right, the next thing we do is we copy from C. Now what's C here? In this case, C is an X value. It's an R value that's a move from L value, I'm going to say, or a stood move of an L value. So this should say what? It should say move. As we copy from that particular C, we should move from that because that's what the caller said. And in fact, that's what we see happen. We have the move constructor done for C. Finally, we're going to copy from all the others in one shot. D, E, and F are a string that is an L value, so we should copy that one. And int 42, which we just passed by value and there's no instrumentation. and then a pure R value, a real temporary object of a type string, which we should move. So we should see copy, nothing, move, and that's exactly what we see. So there's an example of in parameters, and you can also try out, and we're still in the process of building the other kinds, in, out, out, move, and forward. They're in various stages of construction, but hopefully that gives you a sense of what this is like, and you can try all these online. So we saw that about 23% of the measured guidance was passing parameters, but another 7% was about initialization, and this is actually, I believe, directly related because of out parameters. Because out parameters reach back to the caller and set a value. Now today, what do we teach? We generally just bail in C++, including in the core guidelines, and say initialize at the point you declare a variable, and that's fine most of the time. If you have a sensible value then. If you don't yet have a sensible value, you have to put in a dummy value. And because that's expensive for big pods and arrays, we always tell people, oh, you know that thing we said about always initialize at declaration? Yeah, except, you don't do that for arrays, for pods, for std array, for example, because that will just generate dummy writes that it turns out optimizers have a hard time getting rid of when you later put in program meaningful values. Putting in dummy values in these cases, we already teach not to do that because they're not useful, because we're going to overwrite them before we hopefully read from them. They're expensive because compilers can't get rid of them very easily, despite many years of trying. And they're error prone because if you have undefined behavior tools that check that you initialize your variables, it will mask the bug because you're actually not initializing your variable when you give it a dummy value at declaration. You're not giving it a program meaningful value. And now the tool can't tell that, well, that wasn't a real value that you shouldn't be trying to read back from. Instead, the holy grail is initialize before you use a variable. And for a local, that just means that if you declare it and it's not yet initialized, like an int on the stack, that you assign to it before you read from it. That's all. And Ada, C#, they do this. Millions of programmers live with these rules, and it works for them, and it finds bugs today that we're not finding in C++. Now, earlier on, I said, today, and we can't really distinguish between in-out and out-only parameters because there's no such thing as an out-only parameter expressible in C++, and that's true with one little exception. The this object in the constructor is effectively an out because the constructor takes a raw buffer of memory and turns it into a constructed object. That is out. So let's revisit the definition of out, and we're going to make one little tweak. Instead of just saying any non-const L value, we'll say that or an uninitialized object. And when you, remember, in every definite first use, you have to assign to it. If X is not initialized, which we are told by the call site, then that becomes a constructor, which basically means, spoiler alert, every function that has an out parameter is in effect a constructor, a named constructor, when you pass it an uninitialized object. So today, we teach std array of byte, which could be hugely big. By the way, and this is not initialized today, that's what the standard says, and you want it to be that way. Then you call it in a loop to get next chunk, and that may or may not fill it. We hope it does, and we test for that. Then we process the data. But get next chunk today, maybe just take an array by reference. We don't enforce in the language not to read from X's contents before writing to them. We don't enforce that we write to it. Now we do those things and we test for them, but the language doesn't say, hey, if it compiles, you did those things. Instead, the proposed equivalent is that I be able to say out on a get next chunk style API, which enforces I don't read from the value before, which knows whether I'm passing in an initialized variable or not. And if I write to it, I will construct it. I'll show you a specific example in a moment, because for array of byte, it's just a pod. So it's just a trivially copyable type, let's say, a trivially assignable. So constructor has a slightly less interesting meaning. But I will guarantee that I write to it, including initialize it the first time, and that I won't read from it before I write. And this should be the same if it's an array of byte of 4, not just an array of byte of a million. It should be the same for array byte of 4 as for int, which is the same size on most platforms. And in this proposal, all types, big pods, arrays, ints, have all these same rules. Now, for types today that are initialized at declaration, like say a vector of int, today we call the default constructor. That may not do a whole lot for vector, but it's an example of these dummy writes because we're now going to get value data. That's going to fill the data. But if we could just construct it on the first call to get value, to fill the value into data, then we could eliminate some dead writes already from that vector of int. So the way I'm proposing to opt in to say, no, I want to just allocate enough storage for a vector of int, but not construct it yet. The same as if I wrote int data there, or byte data, to write equals uninitialized. And you'll remember on the previous slides, I put in comments as if equivalently writing equals uninitialized. But there it's already implicit in the language. This would make it consistent throughout the language. And I would enforce that I don't read from the existing value of v, which is the first time through, it's not constructed yet, so that's good. And then when I set it, if v is not already constructed, I will turn that into a constructor call. If it was already constructed, it will be an assignment, and then I will make sure I do that before I read from it. This allows you flexibility. For the last example, let's say it's some other type like database info, and I might want to construct it two different ways. Well, I can't easily say that in C++ today. I can write a lambda that does this and then kind of tries to move the result back, but I can't write alternative constructors easily today, but here I can. I just declare it as uninitialized, give me enough space on the stack for a DB info, and if the main side is there, call one constructor. It's just a function with an out parameter is a constructor. Otherwise, call some other constructor, which in this case just has a different argument, but could be a completely different parameter list with 100 parameters if you wanted to, and it would just work. So here is the entire guidance to an implementer. This is the implementer compiler writer's cheat sheet for what they would have to do. This is in much more detail than we actually have to teach programmers. Programmers is just declare the intent. Do I want an X I can read from, in? When I can read or write, in, out. That I assign to, out. That I move from, move. That I pass along, forward. I would like to have that be in some future C++, maybe 5 or 10 years from now, that's all I have to do to teach parameter passing in C++ or any equivalent language of equivalent power. So empirically, we've seen that parameter passing and initialization are about 23%, at least so far in the guidance I've cataloged. And another 13% is in the kind of class you author. Am I writing a proxy? Am I writing a com class? Am I writing a value type? Am I writing something else? Am I writing a virtual interface or a base class? With this proposal I've talked about today, which is numbered 708 when it gets published, and the metaclasses proposal, which is numbered 707, having actually looked at the rules and analyzed and cataloged and personally read the literature for months, I believe that about 30% of what we teach people about C++ today, we could stop teaching. If we could have those features and then a mode that says don't use the old thing, because as long as the old thing is around, you still have to teach that. But for new code, that we could stop teaching about 30% of what we currently, in fact, teach empirically about C++ if we had intention-based parameter passing, initialization, and metaclasses. So what I've tried to do is contribute an empirical attempt to catalog, classify, count what we teach in the complexity, so we can measure the complexity of C++ and not just say it's complex, but to be even more precise as to how much more, 90%, like Bjarne said, and go well beyond that into exactly where are those sources. And we've talked about how to address two or three of the larger categories, two in particular in this talk, that add up to a potential 30% reduction if you include metaclasses in the other talk. You could read more at my GitHub repo, hsutter/708. That's going to be the paper number when it's published. And it has some examples and test cases. You can go to cppx.godbolt.org and find out and try examples of your own there. Not all of them will work yet, but many of them do. By the way, one last teaser. Answers are in the paper. What would an out this mean? Well, every out parameter can both assign a value, but also construct an uninitialized object. What would operator equal taking in x mean? Well, in means an x I can read from, and if you copy it, knows to copy from L values and automatically moves from R values. So what would writing both mean? Think about it and compare your answer to the paper. Finally, let me summarize many of the CPPCon talks I've given over these last 7 years since I started a systematic effort to look at what are the sources of C++'s complexity and how can we simplify C++. This is talk 7 in that series. I talked about starting, this is in roughly chronological order. I'm going to skip the C++ core guidelines, which is about how to use C++ in a simpler way today, today's C++ in a simpler way. The lifetime proposal, and the paper number is 1179, is about simplifying by directly supporting owners and pointers and eliminate classes of errors, like use after free, use after you invalidate an iterator, to know those things and give you compile time warnings and errors to not make those mistakes. Those have been prototyped and implemented largely, and next steps there is continue the upstreaming in Clang, which has just begun. Another part of this effort is simplifying comparisons to directly express the comparison intent to get rid of boilerplate and errors. That has been adopted into C++20 already, so the next steps there is for implementers to implement it. Metaclasses itself relies on reflection, compile time programming, const eval programming, and code injection. Once you have those, metaclasses themselves become a very thin veneer. That is moving along well. In fact, reflection is advancing well in the committee, and it is one of the very small, the handful of priorities, 6 or 7 priorities, that the committee has formally adopted to give priority to working on in the next 3 years. So that's moving well. And in fact, C++20 const eval, that feature, came directly from the metaclasses prototype implementation. And Andrew Sutton, thank you again. So we're making progress. It's all coming into the standard, and we're on track. Static exception handling, I started talking about 2 years ago. It is not yet prototyped. We got initial feedback from the committee saying this could be a direction that we're interested in exploring. Please answer these hard questions, which we're going to do, and let's build a prototype and let's actually verify you can get these benefits. And then it takes a language extension if it does. So the next step is to say, great, we've now seen there's enough interest to justify doing a prototype, so we'll do that next. And then today, I talked about directly expressing, and I should say, by the way, for why static exception handling, that's simplification, because the greatest fracture point in C++ today is the huge rift between libraries and code and projects that report errors using exceptions and those that disable exceptions. This creates a rift and a fracture point and inconsistencies that I talked about a year or two ago here at this conference. So check this out, and you can see the more in paper 709. And finally, parameter passing, directly express intent. Again, like all of these, simplify the way C++ is actually used by directly expressing intent to get rid of, this case, boilerplate and unify initialization. We are currently partway through prototyping that in Clang. All the prototypes are available at cppx.godbolt.org. So the next steps there is to continue working on that. Now, before the pandemic came, I intended to bring this paper to the committee probably at this next upcoming meeting, which would have been New York 2 months from now, but that's been canceled. We're not meeting face-to-face. I'm not going to try to bring it right now because the committee's bandwidth is reduced. We don't have our face-to-face meetings. We're still making some progress, But the committee needs to focus for now just on those 6 or 7 priorities for this C++23 cycle, not all of which will land in C++23 even without the pandemic. But finishing like the coroutine enabling the standard library, module enabling the standard library to finish C++20, reflection, pattern matching. This is not the time to bring a brand new big proposal to the committee. So I'm going to publish it on GitHub, which I've done. You can find it today. It will be a committee paper, but when the committee has more time again after this pandemic is over and we can have a more normal life, then we'll also be able to make use of what we learned from the prototypes and any feedback that you may have. So please open issues against that repo. Last thought, C++ has always been about efficient abstraction, and I want to emphasize in that order. Too many languages design a great abstraction, like well-designed abstraction even, and then try to make it efficient. That's what made Smalltalk slow with all its messages. It was elegant, but you couldn't make it fast compared to C++. That's what made C++OX concepts fail, because it incurred overheads and then couldn't optimize them away. Instead, learn from what we already do. So I hope with all of the examples I just mentioned in the previous slide, lifetime, how we use owners, owner types and iterators, our pointer-like types are already being used widely. Meta classes, we already have guidance on how to write certain kinds of types. Parameter passing, we have rich guidance on how to pass parameters. Learn from what we've already done, and we've already learned the efficient way to do those things, but by hand. And then for the important ones of those abstractions, we know the efficient way, then make the abstraction, build it into the standard library or even the language as appropriate, so the programmer can directly express the intent, and instead of writing it by hand, it's automated. This describes what I tried to do with metaclasses. It describes exactly what we talked about today with parameter passing and by value exception handling, express intent, and then implement it in an efficient way. So now we're going to switch to John. Please stay here, tuned right here, and John is going to give us the conference wrap-up. Then we'll come back here, and I'll take questions and answers for this talk. John, please.
Thanks a lot, Herb. That's a terrific talk. I'm in this awful position of wanting to say what I want to say, but everybody wanting to get back to the Q&A for your talk. But I really want to thank everybody for being part of this conference. And we'll get into a little bit more of this. I'll have to say, in an important way, this conference is not completely over. So let's dive into the closing remarks. You're going to get a SurveyMonkey today to talk about the talks that you saw today, the sessions you saw today, and then you're going to get another SurveyMonkey that, instead of talking about the specific contents and the specific speakers, we'll talk about the entire conference, all the things that we did this year that were a little bit different. And please take the time to do the survey, because we really, really, really want input on all the things we did differently this time, to think about how to incorporate those into future conferences. And if you're able to give us some feedback, we're going to have what Herb already mentioned. There's going to be a feedback session today right after the Q&A. It's going to be in Zoom, so go to SCAD and get the link there. For those of you who it's already a little bit late and you're not going to be able to stay up that late, we're going to have an early morning one on Saturday, tomorrow, to look at SCAD to see when that is and join us for that. So you can go to either. You're certainly welcome to go to both. I also want to talk about trip reports. I know for most of you, the trip was just from the bedroom to the office, but it was, I hope it was a trip mentally, and I hope it was a trip in an exciting way. If you're planning to do trip reports, whether you're doing it for your blog or you're doing it for your company, if you're willing to make them public, because if you send me the link, I will make it public, because I assume that's why you're doing it. We have a channel here in Slack called Trip Reports, and post anything that you see there, or if it's your own, please post it there. Thank you very much for that. It means an awful lot to help people understand that even an online conference is very much a good use of their time. I want to thank the sponsors. The sponsors kind of took a chance on what kind of conferences is going to be being online, and they stepped up in a big way. And I very much want to thank Bloomberg for being a gold sponsor for us this year. Our other gold sponsor was Quant Lab, first time sponsorship for them, and they've come in a big way, and we very much appreciate that. We had 2 silver sponsors this year, Backtrace and the C++ Alliance. Both have been sponsors before, both continuing a great level of support. We appreciate both of them. We have a number of bronze sponsors: Argo AI, Aspos, Kier Consulting, Esri, Google, Intel, KDAB, Microsoft, Morgan Stanley, and SonarSource. Argo AI, Kier Consulting, Google, Intel, KDAB, Microsoft, and Morgan Stanley are all returning sponsors. Aspos, Esri, and SonarSource are new sponsors for us this year, and we welcome them. I also want to thank all our community sponsors. Again, they have made a tough transition this year from doing most of them. Some of them are actually online forums, which is terrific, or podcasts, which we love. But they've made this tough transition from doing face-to-face kinds of events to doing virtual events, and it is a very different beast, let me tell you. And so I'm very proud of the accomplishments that the entire community has made in adjusting to a pandemic life. I also want to thank some people who've stepped up to provide services for us, including Ceylon, Gaylord Rockies, the Jim Bassnight Band, Jim Roper, and Krieger Event Management, and LSAV Powerhouse. Now, some of you are looking at this and saying, wait a minute, Gaylord Rockies and Krieger Event Management and LSAV Powerhouse? Wait a minute, we didn't have the on-site. We weren't at Gaylord. We didn't use their services. No, you're wrong. We planned an on-site conference, and it's a ton of work to plan an on-site conference, and it's heartbreaking to cancel it. But these teams all came through for us, and it ended up being work that we all had to say, well, some of this might be valuable for next year, but as I said, it was a lot of work. They did great for us, and heartbreakingly, it didn't happen this year. I also want to thank the conference staff. I'm not going to mention all these names. Some of these people you've heard of because you've been working with them through the conference. Some of them are behind the scenes heroes, but this has been a truly heroic effort from my point of view to pull all this together in the way that it has been. And I'm really delighted with all of these people working so hard to support the conference in the way they have. I also want to thank all the content providers. This starts with the program committee. They've evaluated hundreds of submissions, and this year they stepped up to evaluate submissions, some of which were from people who weren't certain if they could actually attend or not, and this was a real challenge for the program committee because of this interesting situation. Those who were approved by the program committee, those main program presenters, they are the core of our content and what has helped build that CPPCon brand, including the daily plenary presenters, which we're very proud of. I want to thank the Lightning Talk presenters and Michael Case, who's the moderator for the Lightning Talk. These have been quite delightful this year. It's really been an experience. And of course, I even want to thank the people who were gracious enough to be on the panel while the Lightning Talks were presented and let us watch their reactions, which what a brilliant idea from Michael on how to make that a kind of a real experience for us. I want to thank everyone who is part of an AMA or a Birds of a Feather or a panel. This also is our tradition to reach out to the community in a number of ways and let people in the community be part of our content. I also very much want to thank the exhibitors. Some of them had formal talks that they gave, but some of them were simply sharing with people in an interactive way. But it's part of the content, it's part of the experience, and we very much thank them for stepping up and being part of our program. And of course, I want to thank Arthur O'Dwyer and the pub quiz. We had 2 of these sessions this year, and it was a terrific addition for those people who were able to participate in that. So thank you all for that. But it turns out content's not quite over. There is more to come. We have at least one new session, and I don't want to dwell on the downside of this, but we had one speaker who, due to a situation, had to withdraw in very short notice. He still is keen to do his talk, so we will announce that. We'll send out an email and say this is when you can appear. So we're actually going to have one new session that we had to pull from the schedule kind of at short notice, but we're still keen to give you that. And because this is an online conference, you don't all have to fly back to Denver in order to attend. as I said, we will announce by email when this happens, and we'll set up and you can attend the session for that. The other thing we're going to do is some follow-up Q&As. We haven't talked very much about this because we still have a lot of details to work out. We don't know how many we'll do. We don't know exactly when they'll happen. We will again be reaching out to you with email. But what we're planning to do is, since there were so many tracks and since you couldn't see them all, what we're going to do is we're going to ask some of the speakers to come to a Remo room, and we will play their recorded session with them in chat so they can talk to you during the session. They can comment on their own talk, and then at the end they will do a live Q&A. And again, we will announce times, and this is part of the conference that we couldn't do at an on-site because we can't call everybody back, but we're going to do this here to give you a little bit more of what you love, which is our content. I want to thank very much our volunteers this year. As you know, they didn't all have the aqua shirts this time, but they really stepped up in a big way. I can't tell you how big a way they stepped up. This conference ran as smoothly as it did because of really heroic efforts of people who learned in a short period of time a lot of technical details, a lot of things that you can screw up and do wrong. Did anybody notice the big screw up in the middle of Herb's talk that I did? It's my fault. Sorry about that, guys. Yeah, it's really easy to get it wrong, and these guys have and gals have stepped up in a big way, and we really appreciate that. I haven't always listed the volunteers by name, but I wanted to give them a little bit of glory. I'm not going to read all the names, but I very much appreciate them. They've been heroes. All right, so I know you guys are really anxious to get back to what Herb has to say. If you can go to a feedback session, we really appreciate it. If you can fill out the surveys, very much appreciate that. And if you are doing a trip report, or if this just inspires you, hey, why not do a trip report, put it on your blog, send it around your company. Please share that with us as well. So thank you very much. And let's come back to Herb.
Welcome back. So I've been looking at your questions, but first of all, let me say the same thing as John, and thank you, John, for helping us put on this conference. Without you, this would not have been possible. And with all of our supporters, including all the volunteers, a personal thank you from me and from the Standard C++ Foundation who put this on. Despite everything, we were able to have CPPCon this year in such a great way. So I really appreciate that. Going to the questions, I'm going to take them mostly in order from the upvoted ones. So please feel free to hit upvote if you haven't already. And the first question, actually the first two are very similar. Wouldn't ABI stability become even harder if an in parameter could change from pass by value to pass by reference at some point because of some small change? The answer is yes, that could be. And so today, you would be changing your pass by value to pass by reference manually so you could see that. But this actually overlaps with the next question, which is, how would I tell the compiler that my type is cheap to copy, or tell it I really want in parameters of it to be by value? I think that both of these, which I have not yet written in the paper, but which is on my to-do list, I think both of these can be addressed the same way. And that is by giving the type a way to opt into how it would like to be passed. And you probably want it by default enable the type author to do that. I can imagine cases where you may want the owner of a system to be able to opt that, to make that choice. One way to do that would simply be to have a trait which defaults in certain ways. So you might, in fact, if you write it as a trait, then we can simply provide the default, the condition for should pass by value, and then you can specialize it for your types. Of course, anytime you hear traits, I say that mostly for familiarity. Remember that these days we would normally spell those instead as const expr functions and overloads and that kind of thing. So those are ways that, yes, I think if there is a way to opt in, then not only can it make it easy to say, hey, here I want my type to be passed by value or not, but it can help address ABI stability as well, while still giving you that automatic optimization for all the many places that use your site. If I have something where I can say it optionally once per type, that's a great place to be. The next question is, how will the parameter description work with inheritance? What if the base abstract method defines an in-out and the implementation does not write to the parameter? So this is a very good example. This was touched on in the talk. So first of all, they have to be consistent. You can't say take an in-out parameter in a base virtual function and override it with an out. So they have to match. The declarations have to match. Otherwise, you're not overriding the virtual function. But if you recall in the talk, or if you go back in the slides, one of the things you'll see is that it says for in-out, the rule is if it's not a virtual function and you didn't write to it on any path, then flag that because you wrote in-out. If you won't ever write to it on any path, then you meant in. You should have written that. But we specifically have carved that exception out if it's not a virtual function, because the way that I think is the right way to think of a virtual function is that the virtual function is its base version and all derived versions together is the function. And of course, that's an open set, because unless you deliberately prevent people from further expanding and extending, that can include functions in the future that aren't even written today. If I can only see part of that set, I can't verify in-out. So by saying in-out, it could be quite reasonable in a base virtual function to happen to have the default implementation not write to the parameter and use the out. But by writing in-out, it leaves the option for derived overrides to be able to do that. So we are declaring the intent and exactly what is allowed. But because we can't see the whole body, we're not going to flag, hey, you never wrote to this in-out parameter. So why did you include the word out? Well, you might have, we just can't see the whole function, because conceptually the whole function is all the overloads that work together. The next question is, do you have a conservative estimation of the time required for the language to evolve in this direction, given the constraint of language feature backwards compatibility, or is this yet another way? Well, there's a few things in here. Any standards proposal of this kind is going to take years. So I've been working on this and getting feedback, as you'll see acknowledged in the paper, from a lot of people already. And this is actually, I first started writing up about 5 years ago. It is now at the point where I feel safe talking publicly about it, because I was going to bring the paper to begin the standardization process, but we're still at the point where the prototype is being implemented. It's pretty complete for in, but we're still working on things like variadics and things like that and virtual functions. So this is going to take some years. And in the talk, I said, I hope that in the next 5 or 10 years, I'll be able to teach just this. So I understand that requires more patience than many have. That's the only way to work in the standards world, is to have patience and be designing things that as you would like them to be a few years from now. Having said that, the other part of the question is a good one too, which is this adding complexity to the language? Absolutely it is. So I bill it a simplification, just like I have with some of my other proposals, which it is. But that's if you don't use the old thing anymore. And there's a legitimate objection that says, well, but for the foreseeable future, old thing code is going to exist, so I will have to still teach that and learn that. Yes, but so there's two answers to that. First, if we get a simplification like this that subsumes and is a replacement for an old thing, just like the using alias completely subsumed all the uses of typedefs, and we can ignore typedefs and use only using in the future, that kind of thing, but more so, then at least for new code, we can teach people to only use the new thing. If you have a C++ whatever compiler, use only the new thing in new code, and then the code that you're writing is simpler, and we can actually provide compiler modes and static analysis checker modes that will warn you if you program outside that subset of the new language, which is smaller, but that's by convention. I hope to have all of these things add up to a place where there's enough critical mass where we can start having a serious conversation about, do we now have enough to subset the language? Now, be very careful with that, because subset does not mean it implicitly means answering the question, are you creating a fracture of the community? And nobody wants to do that. But if you recall Bjarne's talk on Monday, one of the points that he made, especially about the core guidelines in GSL, was a subset of a superset. If we see what's missing in today's C++, like GSL said span was missing, which has now been standardized for bound safe access to arrays. Okay, we add a few things. Then when we have the union of things that has all the things we want, including safety and simplicity and performance, then we can have the conversation about whether to subset and say, well, now if you look at all the new things and for the parts of the language that they are total replacements for, what about having a mode where in my .cpp next file or something, I only program with the new things? So that's a conversation we can begin to have perhaps in the next few years. In the meantime, yes, we're adding and making the language, say, 110% more complex instead of 100%. You're adding 10%, but at least in new code, I'll be able to use the simpler language. And maybe someday we can actually say we have enough of these general things that we can actually start saying, what would it look like to have a world where I program only in the new mode? The next question is, what about when out is optional? So we have a way of saying that. If there is such a thing as optional now in the standard, but if we want to say something in the language, so Titus Winters calls that maybe out. That's actually discussed in the paper. So please look for the string maybe out, maybe underscore out, I think it is, in the paper. And I believe I put in discussion of that. But basically, that's okay. You can say that with in out, because the rule is, as long as there's some path that you write to, that's sufficient for in out. It's for you to satisfy that you really didn't mean an in parameter, because you could do an out operation, but not every path is required to do that. And if you want to say something stronger of the form like out of optional, you can actually say that directly, because you can use the type if you want, if that's the semantics you want to have. Next question, does that mean retiring or deprecating single ref, double ref, const ref syntax, or will it add to just an already fat standard? Well, of course it would add to an already fat standard, yes. But this is like my answer before. Once we have this, so one of the things, I don't remember whether I say in the paper, but I'll go out and say it right now. I personally, from what I've seen so far in the last 5 years of working on this proposal and in conversations with others and looking at the implementation, I think this is a complete replacement for today's how way of describing parameter passing, that you can use only this new way in out, moving forward, and express everything just as efficiently as today and much more simply and with smaller object code. So it's a complete replacement. And then remember that the only reason that we added references in the standard in the language in the first place, ask Bjarne, was for parameter passing. I believe I mentioned this in the 708 document. I definitely mentioned this in my blog post from February of this year, February 2020. Look for references, comma, simply, where I make this point in hopefully fairly blunt detail. So yes, actually, I think that references should only be used largely for parameter passing. We shouldn't be specializing templates on reference types for sure. That's just awful for the reasons I give in the paper. And since with this new style of parameter passing, we don't need references, yes, I do believe that this is a path where we don't need references at all in C++. That's controversial. So go ahead and start sending the hate mail and the angry pitchforks my way. I'm ready for them. But this is the kind of thing we have to think about if we are really going to be serious about simplifying C++ and not just moan about it every year on Reddit and not just talk about it and whoa, how bad things are. If we are going to be serious about simplifying C++, we should be looking for abstractions that directly express the intent of things we already do, bake the important things into the language so that they're automated instead of ad hoc, and that as a result, make other parts of C++ no longer needed, and then we can have a discussion about having a subset that's, as Bjarne has said, really is about 10% the size of today's C++. And yes, this is intentional. It's why I've been working on these things in this way for the last 5 years. What happens with unused parameters, for example, in an abstract-based class? I'm not sure exactly what you mean, but unused parameters should work the same way. If you declare a parameter, an in parameter, and don't read from it, for example, that's fine. Perhaps that's the kind of thing you have in mind. Of course, if you declare an in-out parameter and don't write to it on any path, then you would get an error, and you may need to suppress that in order to say, no, I really did intend that. Which I think is a fair thing to do. I think it's fine for people to be able to write something like attribute suppress this error to say, no, I really didn't mean it, and deliberately opt out of a language rule or a static analyzer rule. That's why the C++ core guidelines do that, and the GSL is we have the suppress for, no, I really mean to do this. That way you can express anything you want, and you can go outside the guardrails if you need to. But now you can grep your code for the places you said, trust me, when there is a problem later, and you can have a better time finding out, okay, here are the places I told the language not to help me, and therefore those are the places I'll look first. Let's take one more question. Let's see. I'll pick this one. With the uninitialized approach, does the assignment now get all the problems of initialization? Think about the chaos of initializing a vector. I think so. So we'll have to see with use cases, but I believe by taking the definite assignment rules that we already have in Ada and C# and other languages where we've shown they work, applying those to C++, and especially you need out parameters to do that. You can't do it easily today. You need out parameters so that you can then delegate construction to a callee. The classic example why you need out parameters, if anybody tells you you don't, say, how do you write get next chunk? There's your poster child example. Then yes, you'll be able to address all the initialization issues I know of, because you will be able to actually require init before use. You must construct an object before, or write to, say, an int before you read from it. And by saying you can do that separately from the declaration for local variables, it lets you also say you can wait until you have a program meaningful value, which most of the time you have at the time you declare the variable, but sometimes you don't, like get next chunk or fill array. And for those cases, which are common when you call C libraries, for example, and for those cases, you will now be able to still get solid guarantees of initialization in it before use, even when you're using those kinds of APIs. So thank you very much again for coming to this talk, to CPPCon in general. Please stay here for a few more minutes and listen to the band, or go to the session that's going to be taking place on Zoom now for looking at CPPCon 2021 to give any feedback you have about this week. And if you are interested in being part of planning, or maybe helping, or at least being a fly on the wall for next year's event. Thank you again for coming. Right here, we'll continue with the band. Safe travels back home, which for many of you will be to your kitchens or bedrooms in your same house. And may we all be safe until we meet again. Thank you again.